Cool. Hi everyone. The last session before lunch, I promise we won't take too long, so you will get to lunch. But before that, let's see what we can do around search and new problems and old problems and all things around search. So I'll talk a bit about like the classic search approach that many of you are using, and then we'll see what new things have come up. Maybe you're using that already, or maybe you've never seen that. We can just dive into those and then develop further. I work for Elastic, the company behind Elasticsearch, where the tagline is, you know, for search. So this entire theme fits very well with our company theme, that we want to search something and find relevant stuff, and I'll show you a bit how. So Elasticsearch, if you've never seen that, uses Lucene, Apache Lucene under the hood, which is like the low-level library that does the actual searching. And then Elasticsearch is kind of like the thing around it that runs it, that provides the query DSL, that provides the distribution, the replication of data, kind of like all the tooling, but the actual searching is very deeply tied to Lucene, though we won't make too much difference between the two as we go along. To make search a bit more concrete, who remembers in Star Wars when in the very first, or the oldest, because numbering is complicated in Star Wars now, in the oldest Star Wars movie, when he was making that hand gesture, what was the quote he was saying at that point? Yes, exactly. These are not the droids you're looking for. And we, by the way, I always forget. Do you want to have a pair of socks? I brought some socks. Is black fine?
Made in Java?
They're more elastic socks than Java socks, I'm afraid. But yeah. Cool. You're welcome. So how search works is, or how this is classic search now, how full text search has always been working in the past. These are not the droids you are looking for, and then I'm using this _analyze endpoint, or let me use my mouse so every screen has it. There is this _analyze endpoint. So here, I'm not actually storing this, I'm just looking at what would happen if I would store this and how this is being processed. So the first step that you normally do is you do an HTML strip, which just removes the emphasis tag that I have in my HTML here, the not, around the not, because nobody's going to search for that emphasis tag, or nobody's going to search for HTML. Then we tokenize. Tokenizing basically means breaking it up at the word boundaries, like spaces and punctuation marks, which is very simple in Western languages. In Asian languages, this gets much more complicated, but in Western languages, this is pretty simple. Then I'm lowercasing everything, because most of the time, you don't really care if something is uppercase or lowercase when you search for it. You just probably lower or type lowercase everything and just search for it. We remove the so-called stop words, and then we stem it down with the so-called snowball stemmer. Stemming basically means reducing something down to the word root. So we're taking a sentence, these are not the droids you're looking for. And what would get stored by full text search would most of the time be something like this. So here, we only have 3 tokens that remain. Droid, you, look. So you can see, we broke up the words. We removed the stop words, so these are all stop words. Stop words are these small words that appear in almost every sentence, but they carry very little meaning. There's not much point in searching for those. You will not really find something interesting with them, so we just drop them. Or you can drop them if that makes sense for your use case. And then we have done the stemming. So droids get stemmed down to droid in the singular, and looking gets stemmed down to look. So it's more or less the word root. By the way, the word root doesn't have to be a proper English word. So many things that end with a Y or IES in the plural would just be stemmed down to an I, which is not a correct word in itself, but it's the word root where it would get stemmed down. So what you would do is you take all your text, you process it like this, and this is what you store. And then when you search for something, you would run through the same pipeline. So if somebody searches for droid, they could then just look for direct matches of droid in your text. And this is both dumb but also very fast. And many things in IT that are dumb but fast work surprisingly well, because this is not doing natural language processing. This doesn't understand your text. It doesn't know what's going on. It's really just processing word by word, and then stores these individual pieces. But this works very well for large pieces of content, and it's just very fast to do. So it is good for many use cases, and it's very easy to understand, but it does have a couple of problems. So for example, if you have synonyms, so multiple words can mean the same thing, it can be a problem, because then you might need to define those because you don't know what somebody would search for. The same problem for homonyms, a word that can mean multiple things. Because you don't capture the intent or what it means, it's really just based on strings, basically, where you search. Also, classic keyword search doesn't work very well if you don't have keywords. Like if you have images or videos or audio, there are no real keywords in those, so it's very hard to extract meaning from them and make them searchable in that regard. And there's generally no user intent. So how do we get to those other things, and how do you do that? That's what generally semantic search is trying to do. So it does focus more, rather than just the lexical meaning of a word, it really cares more about the semantics of what your word is doing. So just to compare the two, previously what we would have to do is we would know the right keywords, and we would always try to hit the right keywords when we search. And this is, by the way, not changing. If you just provide the right keywords and you know exactly what you're looking for, keyword-based search or lexical search is very hard to beat, because it just does the obvious thing. But sometimes you want to describe a bit more what you want, or you want to add more context. So the potential for tomorrow's search basically is that if you provide more context, then you can let the search engine do more work, and it can actually capture what you mean. But this will not work very well if you just provide 1 or 2 or 3 keywords. It's really more about giving the search engine more context, so it can extract that context and then find a similar concept rather than just this. Or let's say you want to do a bathroom renovation, and right now if you want to shop for the right parts, you would need to know exactly, I'm looking for this type of pipe of this material and this diameter and this length and whatever. You would need to search for those exactly, and then you would find what you need. The user intent would be more like, I want to renovate my bathroom, show me what I will need for that. That's really where the semantics might, or hopefully will go to. That is much more support for your search than just trying to hit the right keywords. So how do you implement that? And the implementation is then done through vector search. So you have, back in math, we all remember vectors. And how that kind of works is, you have an input, which is on the left-hand side here. We have images, documents, we have some audio. We transform them into this here. Each one of those is a vector representation. So it's basically an array of floating point values. Those represent our vectors. And each array has hundreds, maybe thousands of dimensions or elements that represent the document. And then when you search, you do the same thing. You also try to find that vector representation, and then you basically try to find which vectors from here are similar to our vector on the right-hand side. And that is what you return. So it's not on exact keyword-based matches anymore, but a similar vector representation. That's the full idea around vector search. So what is a vector? I have this very simple explanation for vectors. Let's say we only have a single dimension, and that is either it's realistic or it's a cartoon. And then we have our 2 Star Wars characters, and you can see that they fall either on realistic or cartoons, depending on where they are. Of course, you will have more than one dimension, you will have multiple dimensions, and they will also in reality not be as nicely labeled. So it's not clear in most vector search models that one dimension exactly represents something, but it is, the vector model has a representation that only itself knows of how to represent your documents. But to keep our example simple, I have humanly readable dimensions, so we have something is more a human or a machine, and then we have realistic and cartoon, and then we have our various characters, and we can draw them out in our vector space, and this is how they are being represented in our vector search engine. So you can see that Leia, for example, is at -1 and 1, so here, and Darth Vader is, well, this one is more cartoonish, but we're not quite sure if he's more machine or human, so he's kind of like sitting in between here. And you can represent any type of character with these. And of course, it doesn't have to be exact on the 0 or 1 values, but I said it's floating values. So for example, maybe Darth Vader is slightly more machine than human, so he's like on this dimension a -0.1. And Luke, because when his hand was cut off, he got this machine hand, he is not exactly human anymore. So he is maybe only 0.8% human anymore. And this would be the vector representation that you want to have. And you will need to have the right model to represent the text that you want to have in your examples. And then it will give you that. And then when you search for something, I want to find who is the closest to Han Solo. And then I basically will get the vector representation of Han Solo, who is probably also very close to Leia because he is realistic and he's human. And so this is what we're searching for. We would have the vector representation of him, and then we get everybody else and who is kind of like the closest in our data model or vector model. And this is the entire idea about vector search, that you can find similar things that are represented through vectors. So I've been saying this word model many times. What is a model after all, or how do I get a model? So generally, everything is a neural network nowadays. So you have an untrained neural network. And for example, then I want to train my neural network that it can detect what is a cat. So I need to give it cat pictures and say, like, this is a cat. And it will learn what a cat looks like. And then I basically have, so this is doing the training here. And at the end, it knows this is a cat or this is not a cat of a picture. And then we have our trained neural network, where you can see here, the bigger bubbles represent, we know the weights of how something should be calculated. And so we have our trained neural network. And then when we add a new picture of something and we ask, like, is this a cat? It will use the trained model, and then it will say at the end, yes, this is a cat, or no, this is not a cat. And this is a very simple example for a model, but this is kind of like how any other model works. It's like you have training data, and then you train the data on something, and then it makes the right decisions, hopefully around that, like, is something a cat, or how should that text be classified, or how can this text represent it? And then with this, you have a representation or an answer at the end. And this is just what we need and do at vector search. How to do that in Elasticsearch is we have a Python library, since most of the machine learning stuff is very Python heavy, which is called eland, and it can take models from Hugging Face, which is probably the most widely used place for open source machine learning models. It can take any model from there, or also your custom ones, and import them into Elasticsearch, and then you can run that model inside Elasticsearch to do actual searching. And natural language processing actually has a lot of different things. So it could also do something like, it could extract like the word or the meaning of a text. This is kind of like what we have done with the Star Wars example, where we want to represent something. It could also do something like a text classification. What type of text is this? It could also do something like question answering. It's like, rather than just giving you the search result page back, it actually tries to answer a question for you. And you can pick it all from a lot of different models. So for example, Microsoft E5 is quite popular nowadays. It also supports multilingual situations. So you can use that with non-English, because a lot of models are just trained on English. For images, OpenAI has a model that it's called Clip that is very popular for images. And the nice thing is it works both for text and images. So you can just add or search for words, and it will match them with images automatically, so that the model has been trained both on images and text. You could also bring your own or have a hybrid approach around those. The main problem around models and all of this is that if your model has not been trained for your use case, it will probably do very poorly. So it's the same thing if you are training to be a marathon runner and somebody puts you on a bike. you might be a great runner, but you're probably not great at riding a bike. And that's the same problem for models. If a model has been trained for one thing, but you're trying to use it for something else, it will not do a very good job in many cases. And that's the biggest problem probably around vector search, is that you need to find a model that fits your use case well, and only then will you get good results out of that. Otherwise, you will have a great model, but not great for your use case, and your results will only be mediocre at best. So how do you actually search vectors? Because I've been hand waving around doing vector search so much. You have data that comes in, and you store the vector representation, and we would normally call that an embedding. So we have your sentences or paragraphs, and they're represented by this array of floating point values. This is the embedding. And when a query comes in, you calculate the embeddings for your documents. You search similar arrays of vectors, or arrays of floats, and then you search those, and then you give them back. So the first thing is you pick a model, you store all your data, and then you search, and then you give back the results of how those results match up. So how does that actually work? So the classic approach would be you have some data source, and then you store that as a document, and then we might have an ID, we have a product name, a description, a price, whatever. This is all classic. These are all the fields as you know them. What you would do if you do this inference step, or generating the embeddings in between, is that we have this, of the description field, we have now an embedding, and this is this array of floating point values, and this could be normally like in the hundreds or low thousands that you would have the representation of the description field. So the description field that says our best selling whatever is represented by this vector. And this is what you would store. And then if you search, your search query is summer clothes, for example, you need to say like, this is the same model that we're using before. And then it basically turns your summer clothes here into a vector representation as well. And it will try to find the most similar vectors on that field that you're searching. You could optionally add any filters. For example, we are only looking for women's clothes here. But this is kind of like the vector search, that you're turning your search query also into a vector, and then try to find the closest vectors overall. So the different pieces and how they all combine is, how do you search? The query is generally called KNN, which stands for K nearest neighbors. And it could be either an approximation or exact ones. Exact matches sound great at first, but they are very expensive and slow. So most of the time you will do approximate nearest neighbor search, or ANN. Though both are subsumized under the KNN term, but most of the time you will do an approximation. So it's not guaranteed that all of those are exact, but you have some parameters that you can tune, and you will basically find a reasonable trade-off between correctness and overhead or speed. How do you store that? You have the field is, we call it a dense vector, but it's this array of vectors or floating point values, and very few of them will be zero. That would be the difference. Like if you have many zeros in something, it's a sparse vector, but here is a dense vector where most of the values are actually filled. And then how to generate that embedding is we have a text embedding model, and that could run externally or within Elasticsearch or whatever your model is and where you could run it. But it's basically generating these arrays of floating point values. And then somebody asked, like, but how does this really work? Because we have been saying, like, we calculate similar vectors, and that's not really how all of this works. So how do you calculate the similarity? There are multiple ways to calculate similarity of vectors. One would be cosine. So we have an orange and an apple, and to keep it simple, we only have 2 dimensions here again. And then we just calculate the angle between those two, and then say, well, these two are relatively close. And if you had something, I don't know, maybe a kiwi would be over here, or meat would be down here, their angle is much larger, so they are further away. So the smaller the angle here, the closer something is. And of course, this doesn't happen just in the 2-dimensional space, but would happen in, I don't know, 700 dimensions, and you'd calculate those. And that's, by the way, also why you do this approximation, because it's very hard to do an exact calculation of all the possible vector combinations. Let's say if you have millions of documents and you want to calculate the vectors between millions of documents, or the cosine between millions of documents, that is a very expensive operation. The nice thing about cosine, by the way, is that you can say these are similar, these are orthogonal, and these are opposites. So the vector actually represents like how close or far apart something is, which can also be a useful attribute for searching. Then there is dot product. If you can use dot product because it's a faster operation, it basically normalizes the length of vectors and then calculates not just like the angle, but basically if I project my A onto B, this is how similar they are. And the model needs to give you normalized representation, or maybe your vector search engine can do that. And then you have a simpler calculation for the vector similarity. And the final one is that I want to show you, there are more by the ways, but I just focus on 3, is Euclidean, where we basically say we have these two vectors and the distance is just the distance from here to here. So here it's not like the angle between them or anything, but it's really just we calculate this distance plus this distance is the Euclidean distance. And there are various other ways how to calculate the distance. For example, one way could be like you calculate both, but you only keep either this is higher or that is higher, and then you only keep the higher value, and that would represent the difference between them. The similarity also often depends on the model. For example, some models require a specific calculation of how do you calculate the similarity between them. And how that actually works in the search engine then, because I said it's like this approximation. So how this works is you have multiple layers, and the highest layer has only a few of the vectors that you have in your data set. This would be all the data in your data set, for example. So you want to search for something, and this is where you want to go, and this is where you start. And basically you iteratively try to get closer. So you come in on the first layer, you find like, oh, here in this space, this is the closest vector. You go down to the next dimension, which is represented here. You find the closest vector to where you want to go, which is somewhere here. You go down to another level, and then it will catch up. So this is here, and then you say this here, in this subset here, this here is the closest vector to what I actually want to search. And you never do all the calculations for these here. So you have multiple layers, and you only kind of like, you try to get closer in each step to get that vector representation. That's why it's only an approximation. And it's a neat trick, and it has a horrible name. It's called HNSW, and I always struggle to pronounce it because it's called Hierarchical Navigable Small Worlds. So you have multiple of these layers. Each layer, like you go from fewer to more vectors, and you kind of like iteratively try to get closer to where you want to go. And that way you don't have to do all those similarity calculations for everything, but only for a subset of the data. And this is how this is fast. One bad thing about this data structure, by the way, is if you have two and you want to merge them, it is a pretty heavy calculation because you cannot just merge that. You basically need to rebuild something new. So this is only one of multiple data structures of how you could do vector search. This is the one that Elasticsearch supports. It has some trade-offs like all the others, but this is the basic functionality of it. And we don't always use that. Sometimes we also use brute force. For example, if you have a very small data set, it's faster to do brute force calculation. So the dashed orange line is the brute force calculation. So that just grows linearly, like it's basically an O of n. And then HNSW scales with an O log of n. So approximately something like this. And so there is a space here where the brute force approach is more performant than the HNSW approach. And we basically do a calculation, and this is this pink line here where we basically draw the line and say like, if it's left, we'll brute force. If it's right, we'll use HNSW. So depending on the size of your problem, it will use different data structures to do the calculations, because sometimes one is faster than the other, and you need to make the right decision or the smart decision to get the most out of that. This is slightly outdated. By now we support 4,000 dimensions. And how many dimensions do you want in vector search? Most of the time when we ask people, they want to say many or more. The problem of that is dimensions have a lot of cost to it. So why you don't want especially to go too wild on the dimensions is because vector search is much more costly than classic keyword search. It needs a lot of memory. So basically for HNSW to work in a performant way, that data needs to be in memory. If you have, let's say, 1,000 dimensions and you have floating point values, so each value of the 1,000 element array needs 4 bytes times 1,000, so you have 4,000 bytes for one single document to represent or for representation. So you need 4 kilobytes of memory just for one document. And then you can calculate, I have 1 million documents, how much memory do you need to actually make that a performant calculation? That's why the number of dimensions gets very expensive. So if you can do something in fewer dimensions, it will be more of an approximation than an exact thing, but it is just saving you cost both in memory but also in calculations. So fewer dimensions are, in terms of speed, often advisable if they give you a reasonable amount of precision. Indexing is slower, and merging those is slower as well. There is a lot of improvements, or there are a lot of improvements happening, but this is definitely heavier than keyword search. One thing that you could do, for example, is you could, rather than using floating point values, which need 4 bytes for each value, you could use byte. Then you would only need 1 value. So what that would look like is, this would be, for example, all the memory that you need when you do the standard calculation. What you could do is, if you say, like, rather than using 4 bytes for floats, you just use byte, you only have like 1/4 of the memory that you need. And then there is, I don't know if you paid more attention in math than me, there's something called principal component analysis, which I either never learned or totally forget until now. But it basically allows you to take only a subset of this data here and only keep track of that and get similar results out of that. And those two combined allow you to have much cheaper vector similarity. It is a bit of a trade-off in precision, but that's normally manageable. It's something like, oh, you save 75% of the cost and you keep 90% of the precision, is for many times a very good use case or trade-off. One quick word about benchmarks, and this is my favorite comic about benchmarking. This is every time some vendor benchmarks their system against some competitor, where they find the right conditions, where they're doing very well and the competition does very poorly, like the squid and the house cat. Because here we are concluding that the squid is much more intelligent than the house cat, and it might not exactly be true. But for that comic or for that benchmark setup, it might work. There is a very good benchmark tool that is done independently by Eric Byrne, and he benchmarks lots of different tools against each other. And that one is pretty interesting and good. We also benchmark a lot internally to see the improvements over time that we make. So for example, since for us everything is Elasticsearch and the Kibana dashboard, here would be an example where the indexing latency, I think we added more multi-threading, and then you can see previously something took like 100 milliseconds to 150 milliseconds or so, and now the query latency is more 50 to 100 milliseconds because there is more multiple threads are involved in a single search here for this case. So we have a lot of these dashboards where we track like how is performance or how is every single change affecting the performance. And then we also have these annotations that say exactly what changed and why does this impact the performance. And this is how we try to make things faster as we go along. Finally, you can combine the two ways of searching. You can combine keyword search and vector search. And sometimes this gives you much better results because sometimes one is better than the other. A general problem is if somebody tries to use vector search, but people are trying to just hit the right keywords and don't provide a lot of context, your vector search will probably not do very well. Vector search really relies on having the right context. But you can just combine them. So you basically take the term-based score and the vector similarity score, you merge them together, and then you give back the overall best results, which could look something like this. So here we do a classic query where we search for summer clothes as the exact matches, and then we also have the vector representation of those, and then we try to give those back. And here we manually say, like, this is only 0.9 times as important as this other one, so you can manually boost those. Or you could even combine more. Like here we have a query search, we have one KNN search on the image, and then we have one vector search or KNN search on the title field. And again, I'm boosting that, say like, this has this relevance, this has 0.5 relevance, and the image is even less relevant. But you can basically, if you have different models which have totally different scores, you need to kind of like manually adjust those. Or there is something called reciprocal rank fusion, or RRF, which basically is a smarter way of blending those together, but that has its own academic paper, and I don't want to go into those details right now. Finally, we have added something ourselves, which is called a sparse encoder, which is not classic keyword search, but it's more like text expansion. What this does is, let's say we have our sentence, these are not the droids you're looking for, and what this gives you is, it expands the tokens on top of what you already have. It adds these other tokens. So it adds ship with a certain like likelihood, and dragon and quest and space and robot. And while some of these are kind of like weird and might not give you the right results, some others like space, for example, might not even be that far off here. And it's basically a model that has learned what should be expanded on any given text. And you don't need to do anything else, and it doesn't do a vector calculation, but afterwards it just uses weights and to find the terms and includes the weight in the total calculation of how relevant something is, and gives you back those results. So that's text expansion. That's another, and that's a sparse model that you can use in this one here. And then finally, there's all this generative AI thing, and then people are like, do I still need search, or do I just generate everything? And that's maybe not exactly true. So here, for example, we have an example where I asked, what is not great about ChatGPT? This was a temporary thing, so it did give you an answer at some point, but it was nice to see that when it errors out on this one, it kind of like steps away from that. So what you want to do is, you ask a question, and you might have your custom business data, and you might take your question, add your custom data as context, then give it to the large language model, and then provide the answer. So the idea here is really, rather than just searching for a direct match or just using a large language model, you can give the custom context to a search engine. And there, by the way, this is the family tree of large language models which have exploded over the last few months, but there are plenty of choices. And I have a very quick example here to show you. So, for example, if I say NASA, most of you assume it's the space agency, right? But NASA within Elastic, for example, means the North and South American sales team, or at least it means North and South America. So here the thing is, I provide that search, I add my own organization's information, and then use that to answer that. Or I could ask, I hope I remember the right question, what does a senior engineer earn? And let's see what we get back. And you can see this is the joy of a large language model, that suddenly it takes much longer. And it says like, oh, I don't know about that. And that is because you're logged in as an engineer right now. So if I would switch that to a manager and ask the same question, and hopefully I get the right answer back. Crap. But, okay. But it has the salary bands because, I don't know, it's not a senior engineer, maybe it's a senior developer. Sometimes it gets that context wrong, but it will find But at least here for the manager, it will then also know that you have or you don't have that information handy. Let me see, what was the right query that I wanted to run here? But that is, by the way, the joy of large language models, that depending on how you prompt them, you can get totally different results. Okay. Okay, and then it gives you the senior level band. So here my large language model answers in a certain way, and by the way, depending on which model you pick, the answers will also be totally different, because different models, different trainings. So you could switch. So this is using in OpenAI right now. Could also use Bedrocks or Vertex, and depending on that, it will give you totally different results, or the answers are very different, even though the underlying documents that we give it for the large language model are the same. So to wrap up, vector search is kind of like this new thing added in the overall search context, but it's not everything. There are many different pieces that you want to have in search, but it's one of the fancy and interesting new additions in the overall search space. And I hope that's the takeaway that you can do from here. So as we say, Elasticsearch, you know, for search. That's it from my side. Any quick questions before lunch? So dense vector, the field of how to store that, has been supported before. The KNN search with the approximation is only supported since 8.0. So before you could do a script score, or you could use a script in a search, and you would have exact an exact search, but that is very slow. So it's not really useful for most scenarios. So you should really have at least 8, but the latest versions have made a lot of improvements, so those are recommended. Those have this approximate nearest neighbor search. So that's only available since 8, so that's the recommended version for that, for sure.
And I need to add specific tags in the mappings to say that this field should be taken considerational and vector search. Yeah?
So it will very soon be in the mapping. Right now, it's through an ingest pipeline. So you basically, when you ingest a document or the search, you will need to generate the embedding through an ingest pipeline, and that will do that for you. But very soon, yes, you will be able to say in the mapping, this field is a dense vector field, and it should use this specific model, because you always need to specify the model that you want to use. And then it will, both for storing the data, but also for querying it, it will automatically do the inference for you from that, yes. That's in terms of usability where it should be, and where I don't want to promise any versions, but over the next few months we'll be there. But that's a good question, yeah. Anything else? Otherwise, thanks a lot for joining. If you have questions, find me. I'm around for the rest of the day, and I'm happy to answer. Thanks a lot for joining.